Take a look at the left side of this illustration. We start with raw sugarcane, extracting pure, refined sugar crystals. Now look at the right side. The same separation principles apply in the lab, isolating specific components from blood to detect disease. Both processes deal with mixtures. A mixture is two or more substances occupying the same space, physically combined but never forming a chemical bond. Because they are only physically combined, we can pull them apart. Mastering how to physically separate these substances forms the foundation of modern manufacturing and life-saving medicine. To separate a mixture, we must first classify it. This illustration shows a homogeneous mixture, or a solution, like sugar water. Its composition is perfectly uniform from top to bottom. Every drop is identical. Contrast that with this illustration of a heterogeneous mixture. Here, the composition is not uniform. You can clearly see distinct sand particles suspended in the water, and over time, gravity pulls those heavy pieces to the bottom. So our baseline classification rule relies entirely on physical uniformity. We look at whether the substances distribute evenly or remain distinct. Let's test that visual intuition. We have three mixtures here: salt water, chalk and water, and milk mixed with water. If we pour them through filter paper, which ones do you think will leave a residue behind? As expected, the chalk leaves a heavy residue. It's a suspension, meaning its particles are large enough to be trapped by the microscopic holes in the paper. But the salt water and the milk both pass completely through. Since the milk leaves no residue, you might assume it's a perfectly uniform solution, just like the salt water. To find out, we need a laser. This photograph shows a true solution, salt water. Notice how the laser beam is completely invisible inside the glass. The salt particles are so incredibly small that the light passes right by them without hitting anything. Now look at this photograph of the milk mixture. The laser creates a sharp, bright red line straight through the liquid. The particles of fat and protein in the milk are actually large enough to block and scatter the light toward the camera. This scattering of light is called the Tyndall effect. It proves that milk is a colloid. Colloids are tricky. They look like uniform solutions to the naked eye, but microscopically they are heterogeneous. Human eyes are easily completely deceived by colloids. To reveal the true physical structure of a liquid, we have to rely on physical tests like light scattering. Because mixtures are defined by their physical combinations, we can exploit different physical properties to pull them apart, even when two clear liquids are mixed perfectly together. This diagram outlines a distillation apparatus. It's the standard tool we use when we want to separate two mixed liquids, like acetone and water, that have different boiling points. In the first phase, we apply heat to the boiling flask. The liquid with the lower boiling point, in this case acetone, hits its threshold first, rapidly evaporating into a gas while the water stays liquid. In the second phase, that gas travels down this angled condenser tube. Cold water running around the outside of the tube cools the gas, condensing it back into a pure liquid that drips safely into the receiving flask. By linking a cycle of evaporation to a cycle of condensation, distillation proves we can reliably extract entirely pure substances out of complex liquid mixtures. Ultimately, classifying these mixtures comes down to one precise measurement: particle size. Solutions have particles smaller than 1 nanometer. Colloids range from 1 to 1,000 nanometers, and suspensions contain particles larger than 1,000 nanometers. Let's apply this chart to an exam question. Read this assertion: solutions do not exhibit the Tyndall effect because their particles are larger than 100 nanometers. The first half of that sentence is true. Solutions do not exhibit the Tyndall effect. But the reason is false. Solution particles are smaller than a single nanometer, making them entirely too small to scatter light. From the milk in your refrigerator to the massive chemical plants purifying our water, the microscopic size of particles dictates exactly how we classify, understand, and separate the material world.